Good morning, good afternoon, good evening. This is Dr. Garais. This is BIO117, chapter 21. I tried to rescue our recording from Teams, but I've been under the weather this whole weekend, so I think it automatically deletes it if I don't save it like within 24 hours or something like that. But that's okay. I hope you guys are enjoying your vacation somehow, some way. And let's talk about chapter 21. And we already know about the concept of balance and homeostasis. What goes in has to come out. And we can't have too much of anything, because too much of anything, no matter how good it is, becomes a bad thing. And they're independent. Water and electrolytes, they're independent on each other, because, like, for example, wherever salt goes, water goes, because of osmosis and because of the dynamics of high to low concentration and tonicity and all that stuff, right? And electrons or ions, we already know they are dissolved in water, because remember, water has a partial negative and a partial positive. So positives can get attracted to water, and so can negative ions or anions get attracted to water and get separated in water. So there's always a mechanism in place to replace anything that was either lost and to excrete anything excess. Because remember, when we talked about glomerular filtration and the kidneys, anything extra in your body becomes waste, essentially. And your body fluids are everywhere. And we do know that we're like 2/3 of water. Women have relatively less water than men, because they have more adipose tissue. Nice to know. Not incredibly important to know. Know that the difference between intracellular fluid and extracellular fluid, of course, intracellular fluid, we talked about that in edema. Well, we will be talking about that regarding edema. And that's the fluid that's inside the cells. And of course, your extracellular fluid is the fluid outside of your cells. Right? Extracellular fluid shouldn't be that much. Intracellular fluid, almost, it's more than extracellular. Now, of course, what is extracellular fluid? It's interstitial fluid, blood plasma, lymph, right? And transcellular, which is the fluid in between cells. Now, we mentioned we will be mentioning and showing a picture of intracellular fluid. That's the majority of your body water. But if it exceeds this, and again, don't memorize any numbers, but if it gets out of hand, that's when we have edema. Now, know the difference between extracellular fluids and intracellular fluids. Your extracellular fluids include sodium, chloride, calcium, and bicarbonate ions, while your intracellular fluids include potassium, magnesium, phosphates, and sulfate ions. And know the difference between hydrostatic and osmotic pressure. Hydrostatic pressure is the pressure that is relatively stable, and it fluctuates from here to there. It's in cells and in interstitial fluids. But osmotic pressure, that's the pressure that gets exerted by impermeable solutes. Now, that's the drawing that I did in lecture, where let's look at, and I'm going to do the same thing. Let's find a picture of, here's the one I used for an exam. So when we're talking about tonicity, we're talking about the number of solutes. So let's say the pink is the solvent, of course, is water, and the solute is salt or sodium chloride. So you can see here in this part of this beaker, okay, right? There's way more salt solute. And if there's way more solute, so the tonicity of this side of, and this is your semi-permeable membrane, the tonicity of this side versus this side, this has greater tonicity than this one. And this also exerts way more osmotic pressure because osmoles is, you know, just for now, know that it's like the number of solute or the number of salt particles. So the tonicity is greater here on the right side than the left, and so is the osmotic pressure because there's more things to, and we already talked about like osmosis, right? It goes from where? A high concentration of water here to a relatively lower concentration. So what's going to happen? The water is then going to move across. So wherever salt goes, and there's a whole bunch of salt here on the right side of the beaker, water will follow. And you see that here. Let's bring it back to, what happened to my PowerPoint? There it is. Okay. Now this is the thing we were talking about, the interstitial fluid. And the thing to understand here is everything is going from the pressure of high to low. So let's say this is the arterial and it has oxygen in it. Of course, things are going to go what? Out, because there's way more oxygen in an arterial than, you know, your typical interstitial fluid that's going to be surrounding, you know, your cells and the things that need that oxygen. So you can see here, it can go out, and then there's a balance between the interstitial fluid and the intracellular fluid, or the fluid within the cells. Now you'll also see that this interstitial fluid can get out of hand, right? You're going to have edema, and that's what we talked about, third space sequestration. But for our purposes, interstitial fluid, right? I'm just stating it because one of these days you're going to have clinicals and I'm going to say something like that, and we're going to be talking about edema. Too much fluid here, and you can see higher osmotic pressures here, and it's going to go into lymph, of course. And of course, interstitial fluid, if I have a lot of carbon dioxide here, because, you know, the cells are going to kick that stuff out. Well, more CO2 out here, less CO2 in a venule, right? So, of course, CO2 will leave the interstitial fluid and go into a venule. Water balance, we already know. Thirst intake, thirst centers in your brain, and water output, we already know, is controlled by the kidneys by messing with your salt and your ion balances. Because remember, wherever salt goes, water goes. So let's say, for example, I have way too much water intake, therefore I got to start throwing out some water. Let's say I drank, I don't know, 6 glasses of water, right? Thirst center then picks it up, then what? Tells thirst center then tells the kidney, hey, start throwing out some sodium. I throw out sodium, the water will follow. Daily intake, again, don't worry about numbers, right? But know that the majority of your is from drinking fluid. So you got to drink water, and you got to drink it's close to like 2.5 liters a day. Not enough water. Remember, the majority of urine lost, water lost or water output is your urine. There's a little bit in feces, a little bit in sweat, so that's nice to know, right? And it has to be sensible perspiration. Like you could feel yourself, you know, get sweaty. But number 2 is a lot from evaporation of your lungs, okay? And your skin, stuff that you don't sense. And I just had a tutoring and talked about number 2 would be lungs. Number 1, kidneys. So that is a beautiful question. Osmotic pressure, we already talked about. Osmoreceptors, they're in your hypothalamus. They'll detect changes in the osmotic pressure. It'll detect changes in the sodium chloride solution of things, right? So when the let's say you start losing body water for whatever reason, the osmoreceptors, they'll start stimulating the thirst mechanism. And then of course, blood vessels will also detect water loss as well. And remember, the RAA, renin, angiotensin, aldosterone system will then become activated. If there's low osmotic pressure, if there's low blood volume, or low blood pressure. Osmoreceptors ADH mechanism, again, hypothalamus. ADH is anti-diuretic hormone. So what will it do? During states of dehydration, remember my the story about walking in the desert. Your ADH should be increased because I do not want to lose any more water. So ADH, anti-diuretic hormone, tells your kidneys, do not pee. I need that water. Hold it in. And of course, the exact opposite, ADH will be turned off so that, you can urinate. Excuse me. It's only like 10 o'clock. I'm sleepy for something. Well, not sleepy, yawny. And remember, yawning is your non-respiratory action that has no real clear-cut data on why we yawn. I take things in, I eat things, and then I have to do what? The regulation of electrolyte intake is, of course, in response to hunger and thirst. But the outtake, the output, of course, mostly urine, secondary on your breathing, and a little bit of feces, and a little bit in actual perspiring or perspiration, which is what they call sensible sweat when you're either exercising or on warmer days. So how do you get water and electrolytes? You drink, you eat, right? And mixed with a whole bunch of metabolic reactions, because we know we have enzymes, lipase, we have the proteinases and nucleases and amylases, right? I take in electrolyte intake, and then of course I output them. What's number one? Urine. What's number two? I don't know why they didn't put it in here. It's what? Breathing. The perspiration and feces, they're like, what would they say? 6%? It's not a lot compared. Now, these two very important diagrams are high yield topics. So let's take a pause. Look at them. Let's look at the one on the left first. And that deals with potassium, plasma potassium ion concentration. So if my plasma potassium ion concentration, if K plus increases, that's a problem, because that thing turns things off and I don't want too much of it. So my adrenal cortex, of course, will secrete aldosterone. We already know this. The renal tubules increase reabsorption of sodium ions and then increase the secretion of potassium. Remember, sodium and potassium, they're part of the same pump. So if I am reabsorbing or taking in sodium ions, that means what am I getting rid of? I have to get rid of the potassium, and I throw out the potassium, right? So sodium ions are conserved and potassium ions are then go out into the urine in that order. Next, plasma calcium ion. So when calcium gets low, parathyroid gets stimulated, and then we have the three responses. The number one response is for the bone, osteoclasts, to start breaking down bone so that phosphates and calcium salts then get released into your bloodstream. And then, of course, renal tubules, because of the presence of parathyroid hormone, your kidneys will conserve calcium ions and increase the secretion of phosphate ions. So just like here, sodium and potassium, they get switched off or they get interchanged. Here, calcium and phosphate. And lastly, of course, increased intestinal absorption of calcium ions. Okay? So three things: parathyroid gland, releases parathyroid hormone in response to decreased calcium. So your intestines are told, hey, keep the calcium. Your renal tubules are told, hey, throw out phosphate so we can keep calcium. And then our primary is bone resorption, meaning your bones start breaking down, osteoclasts start breaking down some bone and release phosphate. Acid-base balance, we already know that to death, so I'm not going to go over it here. The only little glitch was pH of 7.35 to 7.45 is what they call physiologic pH, and that's for human beings. Strong acids and weak acids, hydrochloric acid is considered a strong acid. Carbonic acid, which is the hydrogen ion connected to CO2, is a relatively weak acid. Strong base, sodium hydroxide. It's just as strong as hydrochloric acid, but it's a base. And a weak base that we know that's part of our buffer system is this NaHCO3, sodium bicarb. Now, there are three ways that we deal with too much hydrogen ion or an acidic environment. We could use a chemical buffer system. Your respiratory, you can breathe faster and kick out more carbon dioxide, which combines with the H+ ion to make carbonic acid. Or you can urinate it out through renal excretion of hydrogen ions. And remember, the hydrogen ions, they get, they were mentioned that we get rid of them when we talked about the activation of the RAA or renin-angiotensin-aldosterone system. So what are chemical buffers? One classical one is they're weak acids or weak bases. And one example of a weak base, bicarbonate. Another example of a weak base is phosphate, hence the term phosphate buffer system. And last but not least, any protein, plasma protein, albumin, hemoglobin, they also serve as buffers to increase your pH and to lower the concentration of your hydrogen ion. Respiratory center, it is in the brainstem, regulates H+, but you see, what does it really look at? It looks at the increased production of CO2. So they know that you have increased, your brainstem starts figuring out, oh, I have increased production of CO2, which CO2 crosses the blood-brain barrier and goes into your cerebrospinal fluid so that your brainstem then knows what? Hey, that's way too much H+. So what does it do? You have your respiratory center compensatory mechanism, meaning that when your H+ go up, you'll start breathing faster. So it increases the rate and depth of breathing. So it gets rid of the hydrogen ion. So we already know that cells make CO2. It's the byproduct of our phosphorylation, like, in the mitochondria. So of course, CO2 combines with water vapor and specifically the H+, and then makes carbonic acid. Carbonic acid gets released when I breathe. And of course, I also excrete carbon dioxide as well. So think when you're breathing faster, you're throwing out not only carbon dioxide, but H+. And H+ plus carbon dioxide is carbonic acid. Now, we already know that the kidneys kick out hydrogen ion, potassium, and sodium, depending on who's telling them to do what. Well, we have the same thing regarding if my blood's too acidic, my kidneys will then have a signal to get rid of that excess H+. Because remember, too much H+ is now considered a waste. So we don't want anything extra in our body, like too many H+. So your kidneys will start throwing them out. Anything low pH of 7.35, you have, my patient is acidosis. The diagnosis is acidemia. The exact opposite, pH above 7.45 is considered alkalosis, and diagnosis would be alkalemia, or too much base or alkaline in my blood. This is too much acid in my blood. You can see here, like 6.8, pretty bad. 8, pretty bad alkalosis. And buffers and breathing tend to try to make everything where? Between 7.35 or 7.45, which is physiologic pH. We already know respiratory acidosis. My patient will start breathing what? Fast and have dyspnea. Right? Okay, it's respiratory acidosis. Metabolic acidosis, we have too much acid, too much H+. Your kidney will now do what? Start secreting H+. Okay? You do not need to know the actual causes, the actual pathology. Just know I could ask respiratory acidosis. What does that mean? It goes too much CO2 and H2CO3 levels in my blood. So what am I going to start doing? I'm going to start what? Breathing faster. Metabolic acidosis, I have too much acid, not enough loss of base. My kidneys will then deal with it. And the same thing for respiratory alkalosis. I will start doing what? I'll start breathing slow, right? And as a compensatory mechanism, and metabolic alkalosis, I'll start doing what? My kidneys will start wanting to save hydrogen ions. Okay, and that's what we mean by compensation. I want to do something, my body wants to do something to compensate or to make up for the boo-boo or the pending pathology. So it's constantly pushing your pH back towards the middle, towards physiologic pH. And sorry if I went a little fast, but that's okay. You guys can pause and replay your heart's desire. And I guess I'll see you in class. All right, this is Dr. Garais signing off.